My name is Santosh and I am a student of chemistry honors first year. Here is an audio video lecture of alkyl halides. Intro. The compounds obtained by the replacement of one or more hydrogen atoms of a hydrocarbon by a corresponding number of halogen atoms are known as the halogen derivatives. These derivatives are subdivided as mono, di, tri, tetrahalogen derivatives according to the number of halogen atoms present in the molecule. In addition, the halogen derivatives may be further classified into different classes depending upon the nature of the parent hydrocarbon. There are two main classes which may be further divided as given below. First one is the aliphatic halogen derivatives and the second one are the halogen derivatives of aromatic hydrocarbons. Aliphatic halogen derivatives. These are halogen derivatives of aliphatic hydrocarbons in which one or more hydrogen atom of hydrocarbon have been replaced by an equal number of halogen atoms. Depending upon the nature of aliphatic hydrocarbon, they further divided into three types: haloalkanes, haloalkenes, and haloalkynes. Haloalkanes. The halogen derivatives such as CH3Cl, CH2Cl2, and CHCl3 obtained by the replacement of one or more hydrogen atoms of alkanes are known as the halogen derivatives of alkanes. These compounds are very reactive and undergo numerous reactions which are used in preparation of large number of aliphatic compounds. Monohalogen derivative of alkanes are commonly known as the alkyl halides, as discussed below. Haloalkenes. These are halogen derivatives of alkenes. Monohalogen derivatives of alkenes are known as alkynyl halides. For example, CH2 double bond CHCl, vinyl chloride. Halogen is attached to carbon carrying double bond. And CH2 double bond CH single bond CH2Cl, allyl chloride. Halogen is attached to the carbon alpha to the carbon-carbon double bond. The third one is the haloalkynes. These are halogen derivatives of alkynes. Monohalogen derivatives of alkynes are called alkynyl halides. For example, CH triple bond CCl, the chloroethane, and CH triple bond C CH2Cl, 3-chloroprop 1-ine. The second one are the halogen derivatives of aromatic hydrocarbons. These are halogen derivatives obtained by the replacement of one or more hydrogen atoms of aromatic hydrocarbons by halogen atoms. These may be subdivided as nuclear substituted derivatives and side chain substituted derivatives. The nuclear substituted derivatives are: these are the halogen derivatives of aromatic hydrocarbons in which the halogen atom is directly attached to the benzene nucleus. For example, chlorobenzene and orthobromotoluene. Side chain substituted derivatives. These are the halogen derivatives of aromatic hydrocarbons in which the halogen is linked to the carbon of the side chain. For example, benzyl chloride and benzyl dichloride. The side chain derivatives are very reactive compounds which are similar to halogen derivatives of the alkanes. On the other hand, nuclear derivatives are much less reactive and undergo only a few substitution reactions under strong conditions. In this chapter, we shall discuss the chemistry of the alkyl halides. Alkyl halides. Alkyl halides or the monohalogen derivatives of alkanes are the compounds obtained by the replacement of one hydrogen atom of an alkane by a halogen atom. They have the general formula of CnH2n plus 1 X or Rx, where X represents a halogen atom and CnH2n plus 1 or R stands for an alkyl group. For example, methyl chloride, ethyl bromide, or isopropyl iodide. In a wider sense, however, alkyl halides include even side chain monohalogen derivatives of the alkyl benzenes and cycloalkanes. For example, benzyl chloride or cyclohexyl chloride. It must be noted, however, that the compounds containing a halogen directly attached to a benzene ring are in no case covered by the term alkyl halides. Such compounds called aryl halides differ widely from the alkyl halides in their method of preparation and properties and are treated separately. Classification of alkyl halides. Alkyl halides may be further subdivided as the primary, secondary or tertiary halides according as the halogen is attached to a primary, secondary or a tertiary carbon atom. For example, primary halides like N-propyl iodide or isobutyl bromide. Secondary halides, isopropyl chloride or secondary butyl bromide. Tertiary halides. Tertiary butyl bromide, the 2-bromo-2-methyl propane or tertiary pentyl iodide, like 2-iodo-2-methyl butane. Alkyl halides are among us the most reactive organic compounds, as the alkyl halogens can be easily replaced by nucleophilic reagents. Substituted alkyl halides exhibit the properties of the other substituent groups also. For example, benzyl chloride displays the reaction. Benzyl chloride displays the reaction of aromatic nucleus also in addition to the characteristic reactions of the alkyl halides. It may be noted that fluoroderivatives of alkanes, also known as the fluorocarbons, differ from other halogen derivatives in many respects. For this reason, alkyl fluorides and the other fluorocarbons are treated separately from chloro, bromo, and iodo derivatives. As such, we shall confine our discuss to alkyl chlorides, bromides, and iodides only, which are quite similar to each other. Nomenclature. Common system. In this system, individual alkyl halides are named as halides of the particular alkyl group present in the molecule. For example, CH3Cl is named methyl chloride, while CH3CH2I is named as the ethyl iodide, and so on. IUPAC system. According to this system, these compounds are named as given below. The longest straight chain of the carbon atoms, including the carbon which carries the halogen, is selected, and the alkane corresponding to this chain is taken as the parent alkane. The second one is the straight chain is numbered from the end, which gives the smallest number of the carbon carrying the halogen. Third one, the names of the halogen like chloro, bromo, or iodo and the side chains along with their points of attachment are added before the name of the parent alkane. For example, 2-chloro 3,4-dimethyl pentane. The common and IUPAC names of some members are CH3Cl, common name methyl chloride, IUPAC name is chloromethane. CH3CH2Br, common name ethyl bromide, IUPAC name bromoethane. CH3CHI-CH3, common name isopropyl iodide, IUPAC name 2-iodopropane. CCH3CH3CH3Br, tertiary butyl bromide, 2-bromo-2-methyl propane. CH3CCH3CH3CH2Cl, neopentyl chloride, and IUPAC name is 1-chloro-2,2-dimethyl propane. The structural isomerism in the alkyl halides. Higher number of alkyl halides show two types of structural isomerism as given below. The first is the chain isomerism and the second one is the position isomerism. Chain isomerism. Alkyl halides containing 4 or more carbon atoms can exhibit chain isomerism. For example, the two chain isomers of C4H9Cl are as follows: the 1-chlorobutane and 1-chloro-2-methyl propane. Position isomerism. Alkyl halides having 3 or more carbon atoms can exist as position isomerism. For example, C3H7I can exist in the form of two position isomers as given below. The one is 1-iodopropane and the second one is 2-iodopropane. In general, the total number of structural isomers of an alkyl halides is 2n-2, where n is the number of carbon atoms. Thus, there are 4 isomers having the molecular formula C4H9Cl and 8 isomers having the formula C5H11Br. Methods of preparation. The important methods of preparation of haloalkanes are discussed below. First, from alcohols. Haloalkanes are generally prepared by the replacement of hydroxy group of an alcohol by a halogen atom. This can be done by using different halogenating reagents as given below. First, action of hydrogen halides. Alcohols are converted into the haloalkanes by reaction of hydrogen halides under suitable conditions. Like ROH plus HX give rise to RX plus H2O. Primary and secondary alkyl chlorides are obtained by passing HCl gas into corresponding alcohols in the presence of anhydrous zinc chloride, the Grooves process. For example, CH3CH2OH ethanol plus HCl in the presence of anhydride zinc chloride gives chloroethane plus H2O. Tertiary alkyl halides. For example, tertiary alkyl chlorides can, however, be obtained by reaction between tertiary alcohol and concentrated HCl, even in the absence of anhydrous zinc chloride. For example, 2-methyl 2-propanol in the presence of concentrated HCl gives 2-chloro-2-methyl propane. Alkyl bromides and iodides can be obtained by heating the alcohol with the excess of constant boiling HBr 48% or HI 57%. For example, 1-propanol in the presence of HBr give rise to 1-bromopropane, or ethanol in the presence of HI give rise to iodoethane. But in actual practice, hydrogen bromide and iodide are usually prepared in situ during the reaction by using sodium bromide and concentrated sulfuric acid, or potassium iodide and phosphoric acid. For example, CH3CH2OH plus NaBr plus H2SO4 give rise to bromoethane plus H2O plus NaHSO4. CH3OH plus Ki plus S3PO4 give rise to iodomethane plus H2O plus KH2PO4. In the above reactions, the order of reactivity of halogen acids towards alcohol is Hi, then HBr, then HCl. This is because this reaction involves the nucleophilic attack of halide ion on alcohol. Since the order of nucleophilicity of halide ions is I negative, then I negative, then Br negative, then Cl negative. The reactivity of hydrogen halides follow corresponding order like Hi, then HBr, then HCl. The order of reactivity of alcohols towards the halogen acids is tertiary, then secondary, then primary. Majority of these reactions involve the formation of carbocation intermediate. As the order of stability of carbocations is tertiary, then secondary, then primary, the reactivity of alcohols follows the corresponding order, that is tertiary, secondary, primary alcohol. The reaction of HCl with primary and the secondary alcohols requires the use of catalysts such as anhydrous zinc chloride, because both HCl and the primary or secondary alcohols have low reactivity. Anhydrous zinc chloride helps in the cleavage of carbon-oxygen bond of alcohols. Action of phosphor halide. Action of phosphorus halide on alcohol converts them readily into alkyl halides. Like 3ROH plus PX3 give rise to 3RX plus H3PO3, the phosphorus acid. Thus, alkyl chlorides are produced by reaction between alcohols and PCl3 or PCl5. For example, 1-propanol in the presence of PCl5 give rise to 1-chloropropane plus POCl3 plus HCl. Same as 2-propanol in the presence of PCl3 give rise to 2-chloropropane plus H3PO3. In the case of preparation of alkyl bromides and iodides, PB3, PBr3 and PI3 required for the reaction are not very stable compounds, and these are generally produced in situ by the action of red phosphorus on bromide or iodine. That is, phosphorus plus iodine give rise to PI3. CH3CH2CH2OH means 1-propanol plus PI3 give rise to 1-iodopropane plus H3PO3. Action of thionyl chloride. Alkyl chlorides are conveniently obtained by the reaction between thionyl chloride and alcohol in the presence of pyridine. ROH plus SOCl to the thionyl chloride in the presence of pyridine give rise to 3Cl plus SO2 plus HCl. For example, ethanol plus thionyl chloride in the presence of pyridine gives chloroethane plus SO2 plus HCl. Addition of hydrogen halides to alkenes. Addition of hydrogen halides to alkene yield the alkyl halides. For example, ethene plus HI give rise to CH3CH2I, means iodoethane. Propene plus HCl give rise to 2-chloropropane. It may be recalled that in the case of unsymmetrical alkenes, the above addition reactions takes place according to the Markovnikov rule. The rule states that when addition across an unsymmetrical double bond takes place, the positive part of the addendum, the molecule to be added, goes to the carbon atom with the greater number of hydrogen atoms. And it should be remembered that, however, that Markovnikov rule is not always applicable. In the presence of organic peroxides, the addition of HBr, but not HCl or HI, only HBr, to alkenes does not follow the said rule. and this is anti-Markovnikov's addition to alkenes is known as peroxide effect or Karsh effect. Propene plus HBr in the presence of peroxide give rise to 1 bromopropane against the Markovnikov rule, and in the absence of peroxide give rise to 2 bromopropane that follows the Markovnikov rule. Halogenation of alkanes. The direct halogenation of alkanes under the influence of light results in the formation of alkyl halides. For example, methane plus chlorine in the presence of HNO give rise to chloromethane plus HCl. In actual practice, this method results in the formation of mixtures of mono, di, and tri and tetrahalogenated compounds. At the same time, even monohalogenation of higher alkanes gives a mixture of isomeric monosubstituted products. For example, CH3, CH2, CH3 in the presence of chlorine, HNO give rise to N-propyl chloride plus isopropyl chloride. Therefore, this method is used only industrial where complete separation of the mixtures obtained may not be necessary. Iodo and fluoro derivatives are seldom prepared by this method, and this is because iodination is reversible in nature while fluorination takes place explosively. By halide exchange, the Finkelstein reaction. Alkyl halides can be conveniently prepared by treating the corresponding alkyl bromide or chloride with a solution of sodium iodide in acetone. For example, bromoethane plus NaI in the presence of acetone give rise to iodoethane plus NaBr. As compared to sodium iodide, sodium bromide or chloride is less soluble in acetone and gets separated during the course of reaction. As a result, the reaction equilibrium shifts in the forward direction. From silver salts of carboxylic acids, alkyl chlorides and bromides can be prepared by the action of the chlorine or bromine in the silver salts of certain carboxylic acids dissolved in carbon tetrachloride, the Borodine-Hunsdiker reaction. RCOOAg plus Br2 in the presence of CCl4 give rise to RBr plus CO2 plus AgBr, same as silver propanate plus Br2 in the presence of CCl4 give rise to bromoethane plus CO2 plus AgBr. While alkyl bromides can be obtained in fairly good yields by this method, the yields of alkyl chlorides are poor. With iodine, silver salts give esters instead of alkyl iodides. RCOOAg plus I2 in the presence of CCl4 give rise to RCOR plus CO2 plus AgI. Physical properties. The physical state. The lower alkyl halides such as the methyl chloride, methyl bromide and ethyl chloride are colorless gases. Methyl iodide and majority of higher numbers are colorless pleasant smelling liquids. Members with very high molecular weights are solids. Alkyl iodides turn brown on standing due to their decomposition by light. Boiling point. In general, alkyl halides have considerably higher boiling points than the corresponding hydrocarbons. This is due to the fact that alkyl halides have higher molecular masses than the corresponding alkanes and are also polar in nature. Therefore, they have stronger intermolecular forces of attraction than the corresponding alkanes. Amongst the alkyl halides themselves, the following points may be noted. For a given alkyl group, the boiling points of haloalkanes follow the order Ri, Rbr, Rcl. This is because the magnitude of the intermolecular forces decreases with the decrease in the size of the halogen atom. Second one, for a given halogen, the boiling points of alkyl halides increase with increase in the size of alkyl groups. This can be attributed to increase in molecular size, which leads to greater intermolecular attractions. For isomeric alkyl halides, the boiling points decrease with branching, and this is because branching of chain decreases the surface area and consequently the intermolecular forces of attraction becomes weaker. Solubility. Even though they are polar in nature, alkyl halides are insoluble in water. This is because alkyl halides can neither form hydrogen bonds with water nor break the hydrogen bond already existing between water molecules. They are, however, soluble in the organic solvents. Density. Alkyl chlorides are lighter than water, whereas bromides and iodides are heavier than density, being the order Ri, then Rbr, then Rcl. With increasing size of alkyl group, the density goes on decreasing. Chemical properties. Alkyl halides are one of the most reactive classes of the organic compounds. They undergo a variety of synthetically important reactions involving nucleophilic substitution, elimination, reduction, and formation of Grignard reagents. Naturally, therefore, they are regarded as one of the most important synthetic reagents in the organic chemistry. The important reactions of alkyl halides are discussed below. Nucleophilic substitution. The SN reaction. Alkyl halides contain sigma bond between sp3 hybridized carbon and a halogen atom. The halogen atom is more electronegative than the carbon atom attached to it. Therefore, the carbon halogen bond is partially polarized, the carbon acquiring small positive charge and the halogen getting some negative charge. The positively polarized carbon can be easily attacked by a nucleophilic reagent. When an alkyl halide is treated with a strong nucleophilic reagent, the halogen is readily displaced as a halide ion, as shown. Thus, alkyl halides undergo a number of reactions called nucleophilic substitution reactions, in which the halogen is displaced as halide ion by stronger nucleophilic reagents, giving a large variety of products. The nucleophilic reagent may be a negatively charged ion such as OH negative, CN negative, or OR, generally added in the form of its sodium or potassium salt, or a neutral molecule having an atom with a lone pair of electrons such as NH3 and RNH2. The halogen atom which departs along with the bonding pair of electrons is known as the leaving group. It may be seen that in the nucleophilic substitution reaction, the carbon-halogen bond undergoes heterolytic cleavage and lone pair of electrons of the nucleophile is used to form a new bond with the carbon atom. Order of reactivity with respect of halogen. The strength of carbon-halogen bond is different alkyl halides, and therefore the reactivity of alkyl halides depends upon the nature of the halogen atom. It is found that the carbon-halogen bond strength follows the order CF, then CCl, then CBr, then Ci. The CF bond has the smallest bond length due to the small size of fluorine, and therefore it has the maximum strength. As the bond length goes on increasing with the size of the halogen atom, bond strength goes on decreasing. Since carbon iodine bond is the least strong, it is broken most easily, so that the alkyl halides are the most reactive and the reactivity decreases in the order Ri, then Rbr, then Rcl, then Rf. In the other words, it can be said that iodide ion departs from the alkyl halides most readily and is the best leaving group. The order of ease of elimination of the leaving groups is I negative, Br negative, Cl negative, and